I'm ready.
Okay. So, hi, everybody. This is our last actual class of the semester before the poster presentations next week. And I'm happy to introduce our guest speaker today, Beidi Chen. And she is a assistant professor in the ECE department and has done a lot of work on exactly what she's going to talk about today, which is efficient methods for long context LLMs. So I'll let you go ahead.
Thanks, Ren. All right, can everybody hear me? Cool. Okay, so today we're gonna, I think I look at the syllabus and then we'll know a lot of things about LLMs and then also like transformer architectures and fine tuning. And the last lecture, I think is about like inference and different knowledge about that. And today I'm gonna focus on the long context LLMs and what's the kind of the challenges regarding the capabilities and also the efficiency. Just like the title. All right. To motivate a little bit, so long context LLMs, why is it very important? For example, is embedding in this personalized assistance. For example, the ChatGPT you probably use every day, and you realize that you always input, maybe you dump a paper, like a PDF or something to it, and it's super long context, or you have like interactive conversation with it. And also they're like program automation. For example, if you expect the Copilot to have like your whole like code base and then help you that to fix some bugs or make some recommendations. And that's usually like a really long context, right? And then also like the AI agents. And we kind of see that maybe 2 years ago when the LLMs just kind of started, the context length by default is like 4K, 8K, and so on. And it's really long already. You can't really like write more than 8K in a couple of hours, right? And but now 128K from the state of art open source model is kind of like a norm. And for example, like Gemini Pro 1.5 is even have like 1 million context length, right? So now is like a norm, what we call it long context a few years ago. So it is very useful and people find applications on it. So what are the main challenges? So we first go through like from the system perspective or from the efficiency perspective, what is difference between, like you probably heard a lot of kind of quantization, pruning, and all the rest on the pre-LM era, right? So what are the challenges on the LM era? Why is it different? And why we're restarting this topic? So this is like the first type of challenge we're going to present. But throughout the talk, we're going to see other challenges on, for example, what are the kind of long context capabilities people expect? For example, like, is it like very long relations you want the LMs to reason about, or some hidden relations you wanted to kind of extract? But does the LM do a good job there? And does any work which solves the efficiency problem, does that kind of sacrifice some of the like better abilities that we expect LM over RAG to solve, right? So let's get started. So one of the main challenge is the memory IO. Why is this special? First of all, before the LM, we don't see kind of like the model weights and like KV cache will introduce later, this kind of memory challenge to be like 400 gigabytes. Like, for example, the state of art, the GPU is like 80 gigabytes, right? Even to load them into your GPU main memory to contain them, that's a big effort. Before that, we don't see this kind of challenge. The second one is like this KV cache. This is a special kind of I would say a bottleneck for autoregressive model. So we kind of observe that when ChatGPT generate things is like one token by token, right? So every time you generate one token, you have to cache something so that to avoid some recomputation. We're gonna see the details later, but this is very special for autoregressive. For BERT, you don't have that. Okay, so for LM, for the generated models, you have that. And that is linear growing with your sequence length and batch size. So I gave an example there. So if you think the parameters are the memory bottleneck, the KV cache is even worse. Because like even you use a lot of optimization from the training, like GQ8 and all the rest, you still have possibly like larger KV cache than the model, and it is growing. Okay. And the second one is the low parallelizability. So if you just load it once, that's not a big problem, right? But the bad news is you have to load every single time you generate one token for this two. So that's why it's becoming a kind of efficiency bottleneck. And it's not about loading from CPU to GPU. It's already contained on GPU. But when you compute anything, you have to load them from GPU to like your compute unit. So that's why it's taking time. The latency and throughput are kind of bounded by this. All right. Therefore, we kind of need or design more efficient algorithm and system to deal with this long context inference. A little bit more background about why this is very special and why NVIDIA doesn't like it is because what is our GPUs good for? They are good for kind of computation, right? Their flops are really, really high because they can do all the parallel computations. But what does this memory overhead bring? So this memory overhead is like everything is like memory bounds. So it depends on how fast you load data from your GPU memory to compute unit. It's not about how fast you do the computation, which means that it gives other kind of hardware community or new hardware opportunities, because it's not about CUDA, it's not about like flops high, but it's about how fast is memory bandwidth. If you hear about some of the, like, for example, Grok and some new hardware, is about how they save this like memory loading overhead, okay? And this is related to what we're gonna present, like the second work we're gonna present is very related to this. So I just bring it up now. All right, so let's see a couple of work developed by the group on how to overcome or how to trying to address this overhead. We tried many attempts, and what are the like our journey is, I'm gonna share with you. The first line of work is kind of trying to do that on GPU, like just using this 80 gig or 24 gig, depends on how much we have. What are the things we could do? And the second part is what other things we can do with GPU and CPU. I just mentioned about GPU might not be very good at this kind of task, which is memory bound. And maybe with the help of CPU, you can leverage, like CPU is very large and its memory bandwidth is not very low. It's only 10x slower. Auto computation is like 100 times slower, but memory bandwidth was okay. And then how do we leverage that? And this is co-designing with the algorithms and some insights of the modeling, and especially in the long context setting. All right, let's get started. So the first attempt is kind of in the category of static KV compression. So what do I mean? So some background about what is KV cache bottleneck. So I think throughout the lectures, you know that the attention is the key mechanisms and architecture of transformers, which are the backbone of all these generated models, right? And then specifically, there are two matrix modifications which are very important, which is the softmax QK transpose. And after this, computing the attention score, which kind of like, if you see the higher or the darker color just represents higher interactions of the tokens, right? And then you're gonna do a weighted sum on the V matrix, which kind of saying that by generating the next token, like I want to eat an apple, what's the next token? What are kind of like the ways I should be weighted with my previous context, that kind of feeling, right? Of course, you are gonna do that many layers and many head, but that was the intuition. So as an example here, I love randomized. If I want to generate the next token, like algorithms, what are the computations I need? First of all, this is my context. I love randomized. There are like Q matrices, right? It's 3 by D. And then there's key matrices as well, which is also 3 by D. So when I generate these algorithms, we're gonna see like what are the repetitive computation we need to do here is basically we don't need to recompute this 3 by 3 attention matrix again, and also in the MLP side, because autoregressive model says that if you don't change your future generation won't affect the previous ones. So you can just cache all the case so that you only compute the row of the attention matrix and the new ones with the previous ones, right? So you don't have to recompute the whole thing. So that's the kind of trading off, like cache is kind of, you trade off memory for compute. So what are the existing approaches and challenges? It's actually a widely studied field on, for example, when GPT-3 was developed, I think it was covered in a lecture as well, that sparse transformers are kind of trying to resolve this problem. They knew that this attention in the inference time, the KV cache will become a problem. So try to make it a constant. They have this like weird shape, but if you look at the K cache, it's sliding and they're fixed positions, which means that you don't need to save like linear to the sequence length type of vectors, right? So they do that design. So that problem is if you don't do that in the training and the inference, which people believe that the sparse transformers, the sparse fixed sparse attention are kind of sacrificing the ability of the model. So they don't do that in the training anymore. But if you do that in the inference, which means that you're gonna just sacrifice the accuracy as well. And then we know there's like great work on like flash attention reformer, that kind of attention either like exact calculation or some kind of approximation which is dynamic is better. Right? People do that in the training, but the problem is those do not fix your inference problem. So no matter you use flash attention or not, it's not gonna save how much memory you have for the KV cache, right? So it's saving the attention matrix calculation, but it's not saving the KV. And the other ones are like, if it's like super long document and you want to ask like 100 questions on it, what we can do is we can just compress it once and then query it many times. That's worth it, right? But usually, do you do that when you do like online interaction? You usually don't. But in specific applications, this expensive eviction policy will work, but usually it doesn't. So ideally, we want some kind of cache, which is a small size and accurate and also like low cost, right? And the first kind of work we develop in the lab is like first identify this is a bottleneck and this will be a future bottleneck, which we're right now, right? It's becoming a more and more bottleneck now. But the observation is, attention is probably sparse, which means that there are some computations we can save. Kind of saying that when I generate the Apple or the algorithms, I don't need to look at all the kind of context for that specific generation, right? It is probably sparse. So when it's sparse, then there's opportunity on potentially we could probably save like 20x if it's like 5% sparse, right? Or dense. But what are the challenges? We identify the challenge on like, how do you know that if you throw away some of the cache or tokens, you're never gonna use it later, right? You have to predetermine, I don't need this Apple anymore, which is hard. Maybe you're gonna ask some questions about the Apple, right? So what we found is actually pretty interesting on what you're gonna use now, which has like higher attention or scores. If you look at the kind of summation of the column, you're likely to reuse it later. So for example, for a fixed 500 tokens, if you don't receive any attention now, it's highly likely you're not going to receive any attention in a future generation as well. So that was the observation that we have. So the first one is very simple. We just calculate the scores, accumulate the scores. And then when we are out of memory, we just throw away the lowest scores ones. And it kind of works in some of the applications, and especially like summarization or the rest, like the easy ones don't need too much kind of ability of the models. So it works. So, and then we're curious, like, why that happens? What are these heavy hitters that everybody's just going to look at, and then they're going to be persistent, and in the future generation, they're also going to be looked at. So what are these, right? Then we're going to kind of find this interesting phenomenon. It's called attention sink. It's basically that the top 1 or 2 tokens are the first and the second ones. So if you look at the attention map, they have a weird kind of attention to the very first 1 or 2 tokens. Then we may hypothesize. So first of all, maybe something semantic happening. For example, when I say something, or when I start the beginning of the class, maybe the first sentence is very important, right? Maybe the starting things are important. And in the end, what we tested is they're not. They're not semantically important, because even we switch the first token or several tokens to be like new lines, they're still important. So there's some bias into it. We were going to cover more later, but at that point in this work, we just discovered there's a bias in the first several tokens, and then maybe is kind of introduced because of the training of the softmax. For example, imagine if you don't want to look at anyone, there's no attention. For the softmax mechanism of the attention, you cannot go to 0, right? You have to be uniform. That's the lowest you can reach. However, if you have a junk token, or we call it sync token, so when you don't know who to look at, we just look at the first one because it's an autoregressive model. Only the first one can be looked at by everyone, right? And then that's making it like this dynamic system more stable. So that was our hypothesis at that point. And then based on that, we're just saying that, okay, you can probably extend it to like 4 million tokens because you can just keep sliding. And as long as you're focusing on the first token and the local token, you won't fail. The perplexity won't just explode, right? But of course, when you look at the first several, like the first 2 work, you will realize that they will forget some of the contents, right? So evicting them or like citing window auto-rest, they may be capturing very important contents, but they will. Like what I just give an example. If you talk about, if nobody cares about the apple, but what if you ask a question about the apple later, right? You will get evicted. So you will get invoked. So what do we do? So we try very, very hard, a line of work on not throwing away like those KV cache or tokens. Instead, we kind of compress it to the constant memory. There are ways to do that. You can quantize them. You can do convolution. You can do orient. All of them are kind of trying to bring down the memory consumption of the unimportant tokens. However, what we discuss is they still fail in many cases that we actually want or expect the long context model to do. As an example, if you want to do like 1 million contacts, why don't you just do RAG? Because you can just split the 1 million contacts into chunks. And then when you ask a question, you can probably just do some kind of RAG on the context level, and then do a comparatively shorter context modeling, right? Like why and when do you actually need a long context modeling? It is deriving some of the relation that is actually embedded in your context, and using simple retrieval won't solve that problem, right? We'll give an example here. This is a very like symbolic example, but let's give you an intuition. For example, if your derivation just need V0, V2, V1, V, you have to do like several logic steps to derive a variable. Then you cannot like simply solve it with RAG because all of them are necessary. All your contacts are necessary to derive a relation, right? This is a given example. You can replace this V0 as like an animal name, or this relation as like A is B's father and this, right? You can replace that. This is a symbolic example just to say that when you really need the whole context to understand some relations, and this is where long context is doing better than RAG, and this is the ability that you don't want to lose if you want to do a compression on it, right? You spend so much compute and time to train a long context model, and you expect it to do something that is amazing. And then you, in the compression, although dealing with the efficiency problem, you don't want it to be hurting the ability you're looking for. So that was an example. So for example, you will start mixing like V's and then doing some mistakes. So this static KV compression will succeed in, for example, like summarization, question answering, simple examples. But when the logics are more complicated, and when you're solving more complex problems, it will just fail, right? You pay the price. So the compressed information will never come back, basically. And what is even more challenging here is we realize even the ceiling of all this compression method, which is top K. I just talked about the all line of work is based on observation that attention is sparse. What if it's not? So the sparse means that you just compute the attention and then look at who are the top like 10% or like 20% like tokens you're gonna look into, right? And you expect at least those will work. But we tested on the the benchmarks, for example, like frequency word counting, and then the previous, this kind of example, which is a new data set I'll talk about later, we developed, it would just fail. When it's getting more complex or leveraging the full context, it starts to fail. So this gives us a kind of a very strong signal on even the ceiling of all this approximation method will fail. And don't even mention that you can't reach this ceiling because you can't compute all the top K and then select, right? So which is kind of very worrying. And then what do we do? So the first attempt is, the key observation is when the KV cache becomes the bottleneck, maybe there's another way which we can do like lossless compression. We talk about lossy compression. They have their own problems, right? But what about lossless compression? If I don't change my output, can I do something better? And this is related to the line of work in speculative decoding. Maybe it's covered in the previous lecture, but I'll just give a very simple intuition. So usually what speculative decoding was for is you have such a large model and you don't expect it, you don't expect a small model trying to like simulate this large model to be every time correct. But as long as, let's say you generate 10 tokens and 4 of them are correct, that's good enough, right? Because your small model compared to the large model are kind of can be kind of ignored. And then what is leveraging is what I covered at the beginning of the class. So these models, and especially the attention and related to the KV cache, is very, very memory bound. So it's not leveraging the GPU, the cores, and computations. So speculative decoding is leveraging the fact that decoding 1 token and verifying 100 tokens takes the same time. So why don't you just load it once and do more computation on it? It will take the same time anyway, right? So why we can leverage speculative decoding in the long context learning setting is because KV cache becomes the bottleneck. If you look at if you still remember the memory analyze that we present, so it's easily kind of start to dominate even the weight, like the memory size of the weights, right? So which means that KV cache will actually become the bottleneck. And what is the difference between a small model, let's say like 100M model to speculate a 7B model versus 1% or like 10% of the KV cache to speculate the KV cache? The accuracy. Because of the scaling law, it's very, very hard for a 100 million parameter model to be as accurate as a 7B model. But the KV cache is different. Let's say we have a model of a 7B with the full KV cache and 7B with 1% of the top KV cache. There's opportunity because KV cache can be like 99% correct, right? But your 100 model cannot be 99% correct of your 7B model. So there's an opportunity here of leveraging speculative decoding in the long context model, right? And basically we see like kind of the ceiling. We just say that, okay, top K still failed in those reasoning benchmarks or in this complex task. But speculative decoding will preserve your output distribution anyway, so you won't fail. But this top K or a top K base method, like the H2O and StreamLM or top K we just present, can be evaluated another way. It's not about the accuracy of the downstream task. It's more of a what's the acceptance rate, like how accurate your speculation of the original model is. It is very, very high. You never see this kind of number if you're using a small model to speculate a large model, but you see this number if you're using a compressed KV cache to guess what the full model with the full KV cache would do. Like reaching 99%, meaning that 99%, like in expectation, every time you generate 1 token is 99% correct. So you can generate probably like, I don't know, 20 tokens and you get like 14 of them correct. So that's almost like, that's very high, like speed up, right? And what is even better is speculative decoding originally have another concern, which is it doesn't work for larger batch size, which you kind of care about in this serving setting, right? But the long context actually give it an opportunity. I will stay in the kind of the intuition here. So speculative decoding, why it doesn't work for large batch? Because if your batch size is larger, you actually have more computation So your GPU utilization is actually pretty high, right? Let's say your batch size is 100, then it's already full. And doing the verification will actually increase your like decoding time. I just mentioned that for batch size 1 or few, like decoding 1 token and verifying 100 is the same time. But if you're decoding 1 token for 100 examples at the same time, and then do a verification of 100, that's 100 times more. So it's not worth it, right? That becomes a compute bound regime. However, what happens in this KV cache or long context setting is very interesting, because look at this KV cache. We usually call it contextual memory. So which means that it's based on your context and your own example. It does not share across with other examples, right? So for example, for the parameterized memory or the linear memory is shared for different batches or different examples in the same batch. But for the KV cache, you have your own KV cache, which makes it, no matter how large your batch size is, it's always memory bound, because you only do one computation on top of it, right? You don't share. So this gives a chance on speculation still works, and it works even better if your batch size is higher. So that's what this paper is about. All right. However, we're still hitting a dilemma here, right? We just talked about the great work on GPU, which is like you can do dynamic KV compression with speculative decoding is very accurate, or you can do some static KV compression, like throw away things, quantize things, and then compress things. It's less accurate, but it's saving your memory. So is it possible that we can still save memory and also being accurate, right? Which is the next work, or the second part of the discussion is about. It's called MagicPIG. And then in the end, we can realize like CPU as your infinite memory, meaning that we're offloading the kind of KV or attention calculation all on CPU is computed on CPU. And then the other parts, which are more computing intensive, we'll put that on GPU. And this is kind of like the system design. And I will introduce a little bit on why it kind of works. So here is a kind of preview on what usually those numbers are for a GPU and CPU. So you care about the 3 things for your GPU. How fast you do the computation, basically how many cores or your flops number. The second one is how fast you can load a chunk of memory into your computation, right? That's memory bandwidth. And the same for the CPU. So the fact is GPU computes 100 more times faster than CPU, but you load the memory only 10 times. And then this won't change too much because it's just intrinsically hard for the hardware design to grow the memory bandwidth than the flops. And also it's much more expensive. So this is natural. And the other one is like there's a PCIe, which is link GPU and CPU. And that's pretty small. It's only like 32 gigabytes. So the opportunity we see here is maybe we can do a kind of disaggregated computation on, we can do the things that is more compute extensive on GPU, which is more memory bounded on CPU. And we only need to do like 10 times better to make CPU kind of augmented GPU memory, because there's a 10x gap between CPU and GPU memory bandwidth, right? If you want to pretend that CPU is your memory, you have to be like 10x faster with your algorithm. So which means that we have to do at least 10 times dynamic sparse to mitigate this gap. But what is the problem? Remember this. So as long as you are not outputting exactly the same or lossless compression, even the top K will fail. So even your dynamic top K 10% will fail. So is there any way to mitigate this bias? So we show that we need to go beyond top K. So top K is actually not an oracle. It looks like it's an oracle because you compute the attention, you choose the top ones, right? But it is actually not from the estimation perspective. So there's one process that is actually the oracle and is much better than top K. You still compute the attention scores, but instead of deterministically choose the top K examples or the top K case, you actually do sampling corresponding to the sampling probability of your attention score. So let's say you have a attention score of like 0.8, 0.1, 0.005, blah, 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 right? You sort it. And you do sampling. And every time you do sampling, you are kind of doing estimation of your attention QKV already. Let's say the first time you probably sample the V that correspond to this 0.81, and that is your estimation to the current attention, the full QKV calculation. And you sample the second time. Maybe you can also sample the 0.81, or maybe the second time you sample the 0.11, right? And you do that many times. And that is a unbiased estimation of your attention. And this can go beyond top K. And let me give you a concrete example. So why, or the intuition on why this can go beyond top K and in what situation is doing better and why is it unbiased. Let's say we have a zoo and we have 10 pigs, 10 elephants, 10 tigers, and 70 other animals, and each of them have one. And pig, usually each one of the pig will eat like 50 pounds. I'm just making this up, 50 pounds of food. And elephants will eat 20 pounds, and the tigers will eat 10 pounds, and all the other animals will eat 1 pound. And the question is, what is the average weight of the food every animal eats in this zoo? So you're gonna do a calculation on the number of the animals and times how much they eat, and then divide it by the summation, like all of them, right? And the conclusion is it should be like 8.7 pounds, right? So that's usually how you calculate it. And so let's say if we don't know all these numbers, we only know the number of, if we can query the number of the animals, and we can only sample the animal, know the animals corresponding the food or the weight of the food they eat. And this mirroring the top K selection is, let's say our K is 10 or our budget is 10. What do? We will select pig, elephant, and tiger, and another kind of 7 animals, and use them to estimate the average, which is the estimation becomes like 22 pounds. We think based on this observation, we think the average food consumption for every animal is 22 pounds based on the top K estimation. If we do sampling, what do? You will be like building a distribution, right? Now you see that there are 10 pigs, so the probability is 0.1, and you have 10 elephants, it's also 0.1, and so on and so forth. And you sample from that distribution. And the first time you probably sample an elephant because it has probably the highest probability. The second time you probably sample a pig, third time a tiger, and other 7. So this is a one example trial. It's not saying that every time you will sample this trial, right? You will probably sample different ones. There's a variance. But this kind of satisfies the probability that they sample from, right? And then you can estimate the average by the first time you do estimation. I think this whole zoo, everyone eats 50 pounds because I look at the pig, they eat 50 pounds. The second time you look at the elephant, they're 20. And the third time you look at the tiger is 10, right? And you continue to sample. And based on this, and you sample 10 times, so you divide by 10. So with this estimation, you can get exact 8.7 pounds, right? But there are variations, there are variance, right? It's not every time you sample this, but with more samples, your variance will go down, will increasingly go down. So this is an intuition on if you map the number of pigs or number of elephants mapped to the attention scores. And if you map the pounds, like 50 pounds, 20 pounds to V, this is exactly how you kind of do this estimation with your attention, right? The attention is also calculating a weighted average of the previous tokens, right? All right. So basically what I'm trying to motivate here is we need some mechanism which can do sampling instead of exact or deterministic top K search. So this goes to like algorithms in the 90s called locality-sensitive hashing. So what this algorithm can do is, for example, you have a query in this 2-dimensional space, which is a circle. and you have a nearest neighbor, which is another data point, and you have a far away point. So what this algorithm do is, if you randomly split with a hyperplane, there's a probability that you're gonna split your query and its nearest neighbor and your query and further away points, right? But you can observe that no matter how you cut it, the probability that you're gonna separate your query and your far away point is higher and is proportional to the angle size, right? So what is it kind of saying is, it's likely to separate far away points and unlikely to separate the near points, and you can exactly calculate the probability. This is very important in the previous context, because remember, we want something that can do sampling. Sampling means that you know what is the probability you sample an item, right? And we use this hashing algorithm to do near neighbor search. And how do we do that? Usually is you pre-process your data with the hash functions I just talked about. I present like one hash partition, but you can do that many times, right? And then you can pre-process this into like hash tables. How to do that is, let's say your 3 and 6, I partition them many times, and they still have the same hash code. They never been separated. Then in the same hash table, they're gonna be in the same bucket, right? And you can calculate this probability exactly based on their cosine similarity, right? And then in the query phase, or how do I do search, is usually you do the same thing with the same hash function, these partitions, with your query. And you see where you're gonna partition your query to and what are the buckets. And then from this, you kind of know who are my near neighbors. And this is data independent, kind of a near neighbor search method. And what is difference is, I will jump through how to do the matrix multiplication on it. But basically, you can use hashing to regard your Q, your QKV's Q as your query, and your K as your data. And you can do sampling on the top of it, and you can exactly calculate what's the sampling probability given this Q, right? So that is very, very close to the process we just described in the zoo example, right? Except for the probability distribution is not exactly the attention score, but is kind of monotonic to it. That's good enough, backed up by the theory. It's kind of related to the line of work in importance sampling, which means that if your proposal distribution, your target distribution have a similar mode or like peak, is a good enough estimation. So that's how we do the estimation here. And basically, we're just gonna show that how do we leverage this in the MagicPIG design. So basically, we can just put hash functions calculation on GPU, because it's also kind of compute intensive, right? You're gonna compute many hashes. And then you're gonna position or put your hash tables on CPU, because they're occupying much memory. And you also do the hash table lookup on your CPU. And then you're also gonna, after you look up, you'll decide what are the case I'm gonna calculate and what is the probability of it. With that, you can do a unbiased estimation of your attention score. And you do that part on CPU, because we just mentioned that CPU's memory bandwidth is pretty good. It's only 10 times worse. And you can do super sparse here, so which mitigate this gap, okay? And then you can aggregate some of the partial attention, for example, the sync or the local ones you just generate on GPU, and do a unbiased estimation in the end and pass them back to GPU. And then I don't know if you heard this like ruler benchmark was about like evaluating how effective your low context is. Recently, we used another paper we're gonna present later, like the factor, which is another benchmark. Actually, a ruler can be cracked with a lot of kind of RAG variants. So it is testing the effective context lens, but you can also hack it without giving the full context to the model as well. So that's why that was the motivation. And TopK can work well on this one as well. That's why we start to develop new benchmark as well. We're just develop new method and use new benchmark to attack our method, so that we can keep or increase the ability of the LMs we're approximating. Yeah, this is an example of the other kind of more of a reasoning or complex task that MagicPIG will succeed. And this was the example that I gave earlier with this sampling over top K is gonna work. And from the throughput, you're gonna like improve 2 to 4 times. Another thing I want to note is this is not only working better than the other baselines. It's actually working better than the exact top K oracle. So we're saying that oracle sampling is better than top K, but an implementation or approximation of the oracle sampling does not necessarily go beyond that. But in some of the benchmarks, we see that is actually dominating any method that are kind of leveraging approximate top K because it's doing even better than top K itself because it has bias. And what is this like reasoning data set? It's just a little bit background on it. So the motivation was the long context reasoning ability is very hard to evaluate. For example, the example I gave earlier is like, is it actually better than RAG? In most of the cases, do I actually need the long context models, but not like just do some retrieval on the context level and then fit it into the language models, right? Currently, many tasks can be successful and with some RAG or iterative RAG variants. However, we're trying to see if we can build anything. We still believe that long context models have its advantage. So we want to see where and when it's going to have an advantage. But this evaluation is a very hard thing because of first of the data leakage. You probably know like GSM and all the rest, reasoning ability, mass, but data leakage or contamination sometimes is worrying, right? You don't know if it's doing better or it just knows all the problems. And they are recent work disclosing this as well. And it's also like very hard to standardize the complexity. So as an example, I asked you a question, a math problem that is high school and another problem, which is primary school. Very hard for the machine or for the model to know which one is actually harder because there's not an evaluation by the complexity. It's very hard to standardize this. And the logic is actually pretty easy. And for the ones that we just see, like the rule ones, right? You can just crack it with basically all the retrieval ones or iterative retrieval ones. So it's not very hard or complex relations embedded into it. So which is in contrast to usually the real cases, you expect it to actually do well, reason well, right? And especially now we kind of see like GPT-4.01 was up. And for the models which can do great jobs and increasing capabilities, it's also very hard to train and evaluate them anymore because they seem to do well on all these tasks. So our insight is taken from the formal language, which you have, this is computational graph or automata. So it's very, very related to LM reason. It's not going to the symbolic thing, but it's more of a, can we actually generate infinite data or we define the complexity or the logic depths so that we can at least evaluate how the model are doing from the evaluation perspective. And hopefully, is it possible that we disclose or find some problems of the current model or architecture, then we can improve its training process. And then how we get started is you probably see these examples of V1 and V2. This is just the computational graph on, we can define like relevant and irrelevant computation. For example, they both look like V1, V2, and V100. They look all of them are not noise. They all look relevant. But if I'm just like saying that V1 equals to 3 and V2 equals to V1 plus 1, to calculate V2, I actually don't need V3 to V100, right? So this computational graph just saying that given a problem, I know what is irrelevant and relevant computation or the necessary path. So from this example, I can infinitely generate many variables and relations. So I know how hard is it. The deeper the loop is harder, the complexity is more. And then I also know like what are the irrelevant or how much of the noise is, right? I can precisely define that. And then map into a real example, which make the current pre-trained model to understand. We give it names. For example, there's like South Zoo because there's a hidden relation. Because like, for example, South Zoo's deer, South Zoo's raccoon all belongs to South Zoo's animal. So it's also like requires 3 levels of long context capabilities. First one is memorization, which corresponds to retrieval. You have to at least know what I put in the context. The second one is kind of like common sense reasoning. At least you kind of know that the South Zoo deer and South Zoo raccoon are all from South Zoo. If I ask how many animals are there in the South Zoo, you should calculate these two together, right? That's common sense kind of reasoning. And the third level is more of a logical reasoning. So without knowing what exact number of South Zoo raccoon, I should be able to do a deep calculation to derive it, to answer and add with other animals to answer my final question. And the deeper this logic loop is, the harder my task is. So this is like defining the capability of the long context into 3 levels, from memorization to common sense reasoning to logical reasoning. And the task can be like can be defined as like increased kind of complexity. And let's see several like interesting evaluations on the top of it. All of them are without compression, because even the current full context models start to fail. So we don't, we haven't tested like the full compression models. So you kind of see that there's a decreasing accuracy when n goes up. This n is the effective logic depth. So the harder or the complex the task is decreasing. And then we also evaluate on different kind of real models, not real model, open and closed models. For example, Llama, Mistral, and GPT. And each one has a different decaying rate and starting point. Starting point is kind of saying that even my logical depth is 1 or 0, or I'm just asking to do memorization, how well you are doing. And the kind of the slope means that if I start to add more like complexity of the task, how fast you are decaying, right? And an interesting phenomenon we kind of observe for these long context models on the market is, I think there's a difference between what they train in the pre-training, the sequence length of the pre-training, and the sequence length that's beyond the pre-training. So for example, for the Llama, within the 4K or 8K in their pre-training sequence length, they're doing reasonably well on the levels of like the complexity. But once they do some extension on the context length from 8K to 128K, it seems like they can only do memorization level. They start to lose other abilities. So you can see that. And then what is more interesting is this O1 or this repeated sampling or this training has some secret sauce, because usually what we see is they will start to decay at like 5 logical depths. And if you extend it to chain of thought, you will start to decay or collapse at 10. But this O1 can do 100. So it's a magnitude longer like reasoning depths. So I feel like maybe for a lot of tasks that we ask the GPT-4o1 mini or O1 to do, you don't see a difference because the complexity is not there yet. So because this task will just blindlessly increases complexity. And it's actually very surprising to see it still succeed. It doesn't solve the problem. If it is not to the level of solving the problem still, but it's kind of impressive that extending a magnitude, order of magnitude more depth. Yeah, so I think this is the end of today's talk. And to summarize, we kind of introduce long context modeling. What are the challenges from, for example, the efficiency side, and also what are the current challenge of the evaluation and like the ability side. And then we present several work that could work on GPU and what are the caveats. And then we present a system and an algorithm co-design on GPU and CPU, and present an interesting algorithm which can do this important sampling, which is kind of interesting mathematically as well. And then in the end, we're kind of seeing some details on why we're keep like compressing it, attacking it, compressing it, attacking it, because like to actually make LM work in the real cases and applications, I think the bottleneck is basically the two that we present. One is the efficiency, one is stability. So the reason why it's a little bit hard for now to find a use case is because in some of the use case it could be doing, either its cost is overweighting its usability, or is not to the extent that it can be used for this kind of complicated task. So improving these two back and forth, hopefully will make LM actually useful in many of the cases. All right. Thank you.